So I think last time I'd asked you guys to work on, what is it, 5 through 12? So any kind of questions from there, Grace? Sure. So for 12, we want to start by inputting the data into our calculator. So to input data, I press the Stat button. From the Edit menu, I'm going to select the Edit command. And I already have some stuff in L1 and L2 from doing number 11. So I'm going to start by clearing that data out of there. So I'm going to move my cursor up to the heading L1, press the Clear button, not the Delete button, and then the down arrow. And then repeat the same process, moving my cursor to L2, pressing Clear, not Delete, and then down, and that'll remove all the data. And then I'm just going to type in the data from the table then. So in L1, I'm putting in my elevations. Notice when I typed in 1.0, it automatically just turned that into 1. Don't worry about that kind of thing. And then in the L2, I'm going to put in my population. Again, the zeros at the end of the decimal are going to get dropped. That's not a big deal. And in fact, if you don't want to type them, that's okay. The calculator doesn't know the difference, even though we know from a measurement standpoint there is a difference. Those of you that have been in a science class and talked about significant digits would understand that. Okay. So I got all my data typed in. So I'm going to exit out of here. I guess before I go and I build my linear model, it tells us we're going to be using a linear model, which is fine. I'm going to take a look at the picture anyways, just to get a good idea. So I press second and y equals and just pick the plot 1. I'm going to make sure that's turned on, scatter plot selected. We need to take a moment and think about which one of these is the dependent or independent variables. So here it's the state's population in 2013 and its average elevation. I can't imagine that the amount of people living in a state is going to cause the elevation to change. That seems like a ridiculous claim. Like, it's clearly that the elevation might affect how many people want to live there. So I think that X should be the elevation, Y should be the population. Seems pretty reasonable. So I'm going to press Zoom and then Stat. And this option is a shortcut around having to set the window yourself. So if you pick Zoom and Stat, the calculator will just pick a reasonable window. And now I have a little line left in here. I guess I had some gobbledygook in my calculator, so I'll clear out my y equals menu. And here's my picture. Not great from a linearity standpoint. You guys agree with that? So the model I'm going to expect to get it maybe is going to be kind of poopy, but okay, whatever. That's not the end of the world. Okay, so I'm going to get out of here.
Mr. Gould?
Yes, sir.
Is it too late to show me what you just did right there to get the graph again? The last step to get that graph.
I just pressed Zoom and then Stat.
Okay.
And that gave me the option to, or it just reset my window for me, is basically all it did. But it goes straight to the graph screen after you pick a zoom. So rather than picking my window manually like we did last time, this is just a shortcut to have the calculator do it for me. Is that cool? Or no?
I guess. For now.
Okay. Okay. So that's good. So let's go ahead and build our regression equation out then. So I'm going to exit out of here. I'm going to press the Stat button. and this time go over to the Calc menu. And I'm going to pick from my options linreg. And really, I would always use the first linreg. If you scroll down the list, there's a second one down there. Just use the first one, though. So again, we put our x's in L1, our y's in L2. Our frequency list will always be blank. And then I'm going to store the regression equation somewhere because the question's actually asking us to use this regression equation to make a prediction. And rather than having to type the equation in all over again in my calculator, I'm just going to have it enter it in my calculator somewhere where I can use it. So the place where you can enter an equation is into one of the Y1 spots. So Y1, Y2, Y3, somewhere into the Y equals menu. So to get the Y1, which is the one I'm going to use, it doesn't really matter which one you use. I'm going to press the vars button, which is right here below the down arrow. And since I'm looking for like Y1, Y2, Y3, etc., I'm going to go to the Y variables option here at the top. So I'll move over to the Y variables tab. And in this class, we've only been using the calculator in function mode. So I'm going to pick the function option. And I'm going to pick Y1. And then I'm going to hit calculate. So if I look at what I got here, it says my equation is y equals ax plus b, okay, where the a, or the slope, is negative 2.12, yada, yada, yada. And the b, or the y-intercept, is 13.22, yada, yada, yada. And the r value is the thing that I'm really interested in when it comes to my linear regressions, which is negative 7.4, yada, 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 which is okay. It's not fantastic. I would hope for maybe something a little bit better if I was really going to use this to make predictions, but, you know, it's not bonkers to use it. I'd like that a little closer to -1 maybe, but, you know, it is what it is. This is what we got. So far, so good. So you could copy this stuff down for the equation. Really, you wouldn't want to write it the way the calculator outputs it, though. Write it as the y equals mx plus b equation. So write it as like y equals negative 2.12, yada, 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 x plus 13.22, yada, yada, yada. That's your equation. Like, write it as an equation. Don't write the calculator output down. Is that, we get that? Okay. So it says find a linear regression model. That's what we just did. And then use it to predict the population of a state whose average elevation is 500 feet. So here we have to be a little bit tricky. So I'm going to go back to look at the graph because there's two ways I can do this. And by the way, here's my regression model that's, you can see now if I go hit graph again because I stored it to the y equals menu. It graphed that regression line for me. So I do need to be a little bit careful here about the units. So it says use the model to predict the population of a state whose average elevation is 500 feet. Okay, that's fine. If I look at the table, though, that I used for the data table for this problem, the x variables, the elevations, it says are given in thousands of feet. So 500 feet is half of 1,000. Everybody agree with that? So really the value that I'm going to be inputting for x is going to be 0.5 or 1/2. So when I do that, I get 12.16, yada, yada, yada. So I'd say 12.16 million people, because again, the y variables are listed as population in millions. Yeah, Reese? Yeah. Yeah. And so that was what we did last time. You notice that sometimes when you do that value option, though, you end up getting, you can end up getting an error because you're looking for a point that's off of your screen. You remember that happened last time? We looked at that as an example of something that can happen. I thought about it some more, and there's another way to do that, the same thing on the calculator where you can't get an error. Can I show you guys that right now? So instead of using the graph and using that value option, from the main screen, we can use like a function notation now that we have that equation stored in y1. So if I go and I retrieve that y1 variable again, so I press the vars button, and I go over to yvars, and then select the function option, and select y1. I can do y1 of 0.5 like it's a function, right? Like if I did f of 0.5, you guys remember like function notations from like all your algebra classes to this point? So I'm doing kind of the same notation there. If I do y1 of 0.5, it'll output the value of y1 when 0.5 is x. And the nice part about this is it doesn't matter what the window range is. Like you can't get an error doing this unless like you're doing something like silly, like you put in a subtraction symbol instead of a negative sign for a number, or you did something bonkers like that. But this one you can't run into trouble that way doing it this way. Does that feel okay? As another option, Grace, was it the units? Did you type 500 in for x and like get a bonkers number?
Yeah.
Yeah. Yep. Joe?
Could you do number 6, please?
Sure. It says find a linear function that satisfies the following conditions. Do you want to do this the hard way or the easy way?
Probably the easy way.
Okay. So I'm just going to do this as a regression equation then. So I'm just going to go to my stat menu, and from the edit command or edit tab, I'll pick the edit command, and I'll go ahead and clear out L1 and L2 just like we did before. Because when I see, I guess I should write it down here real quick. You said 6, right?
Yeah. And does this easy way work for all of them?
Yep.
All the problems?
Anything in this format where it wants a linear equation.
Okay.
So when I see g of 4 is equal to 3, I'm just going to interpret that as the point 43. And when I see g of 2 is equal to 4, I'm just going to interpret that as the point 24. So I'm just going to make a list L1 and L2 where the x's are in one column and the y's are in the other column. So I'm just going to do that and then just have it run a regression equation. Oops. So I just did that, right? We'll exit out of here. And I'll do stat calc linreg. I put my x's in L1, my y's in L2, and because all I want is the equation here, it doesn't ask me any prediction questions. I'm not even going to bother storing the regression equation because I don't need it. And then just hit calculate. And there's my answer. Notice that the R value is exactly 1, or negative 1. I lost my calculator there. Negative 1 because, well, there's actually a line that passes through these points. So we just say y equals negative 1/2, or you could write as 0.5 plus 5. And I'm done. Calculated all the heavy lifting for me there. Now, if you wanted to do it the hard way, what's the hard way look like? You're going back to your Algebra 1 class. You're using those 2 points to calculate the slope. And then you use the slope along with one of the points, plug them into your y equals mx plus b equation to solve for b. What we just did on the calculator is, I think, super easy because it's the same process we're doing for like all of these problems. So you can certainly just do it that way. And those of you that have an ACT coming up and like asked to calculate, like write the equation for the line that passes through points, you can do this all on your calculator, and it takes like 10 seconds and like saves you a lot of time. Just FYI. Reese. 9. Yeah, it says, how would you describe the correlation between the temperature and the number of layers a person wears outside? Well, let's think about this, okay? So and let's just kind of not think about us specifically, but just think about a person in general, the average person, because sometimes as teenagers we don't have the best common sense. But if it's really hot outside, are you going to wear like 10 layers of clothing, like a jacket and snow pants and boots and like, no, right? But if it's really cold outside, like it was yesterday morning and it's like 2 degrees or something, are you going outside in like a bathing suit? Heck no. So it seems like there's certainly a relationship, right? That I would say that there's probably some strong correlation between the temperature outside and the number of layers of clothing somebody's wearing. You know, where it's like sub-freezing, you're probably going out in at least 2 layers, you know, like a shirt and a jacket or something. And if it's like past 80 degrees, you're probably going out in only 1 layer, just like a t-shirt or something. You're not wearing like another shirt on top of that. Unless you have like, you know, like some mitigating circumstance, right? Like, oh, I have to go to my job, so I have to wear a suit to work. So even if it's 80 degrees, I still have to wear a suit, like whatever. But that's all. We're just kind of thinking about it in the real world. There's no mathematics to do there. Does that feel okay? As opposed to like, what do you think the correlation would be between the temperature outside and, you know, like what's on television? Yeah, like I don't know that there would be really much to correlate there, right? There's whatever's on television. It seems like it depends on the weather. You know, outside of maybe like a Christmas special or something being only when it's cold out. But I'm pretty sure I've caught a Christmas movie in July every once in a while or whatever. You know, seems like Elf's on all year long.
Can't wait for July. Warm weather. Go outside, play sports.
I know, right?
Freezing.
Yeah. Reese, does that feel okay on what to do with something like that? It's just kind of a thought exercise more so than a, you know, like should these things kind of go together is basically all you're asking yourself, and just using a little bit of logic. Joe?
Sorry, okay. So for the problems, number 8, for example.
Mm-hmm.
So would that be a negative strong correlation?
I would say that's a reasonable answer to that.
Okay.
Yep.
Okay.
Yep. Looks very line-like, and it's going sloping down.
Yeah. So then
So,
it's
yep.
sloping up, positive, sloping down, negative.
Exactly.
Okay. Cool.
That's all there is to it. Okay. Any last questions here on this stuff before we move into the last section here? Yeah. Yeah, so when you've run your linreg and opens that menu where it says store reg EQ is where you do that at. And to get the Y1 to appear there, you press vars, you go over to the YVars tab, select function, and then their list of Ys are there. Is that what you needed? Okay. And again, if you get stuck on any of the calculator stuff, like all the lectures are recorded, so you can always go back and watch the beginning of the lecture and watch me kind of scroll through the calculator stuff again if you need it. All right. Okay, so section 12.3 is basically going to be the same stuff as we've talked about in section 2. We're just going to, instead of just talking about linear regression, we're going to talk about all these other types of regressions here. So linear regression we've talked about. So there's quadratic regression. What would your scatter plot look like for a quadratic regression? You'd want it to look like a parabola, right? Because that's what the graph of a quadratic should look like. Everybody's okay with that idea? There's cubic regressions. What would we want that graph to look like? Well, like a cubic. So you'd want like 2 bends in it. There's exponential. So what does an exponential look like? It starts out kind of flat and then gets real steep. And we're just kind of buzzing through these things because these are all shapes that we should remember from our Algebra 2 class, right? We've talked about quadratics and cubics and exponentials. All of those things we talked about last year in Algebra 2. So those kind of shapes should be rather familiar. There's logarithmic, which just basically looks like a twisted version of the exponential. Anyways, let's see. So quadratic, that would be like an ax squared plus bx plus c. Cubic would be like ax cubed plus bx squared plus cx plus d. Exponential would be like ax to the b. Logarithmic would be y equals, let me think here. They'll probably do it that way. They'll probably do it a times log base b of x. We'll do an example with it in a second. I'm pretty sure that'll be the way how it'll give it to you on the calculator. It's been a minute since I've done one. Now, all of those first 4 we've talked about are all things that we spent like an entire chapter or more dealing with in Algebra 2 last year, right? All those names should sound familiar. The last one is one that we don't spend a good deal of time on. And that's a power model. Oh, sorry. Which is this. And you might say, Mr. Kulik, why is that different than like a polynomial? Right? Doesn't that just look like a polynomial? Here's the dealio. For a power model, that exponent can be any real number. You're not forced, like in a polynomial, to have a non-negative integer. You have to have a positive whole number. In a power model, that number can be anything. Could be a decimal, could be negative, could be a fraction, could be a positive whole number. But you have considerably more flexibility there. What shape would we want for this? Well, really, kind of anything is why the power regression is such a good one, is it's pretty versatile. It can kind of do anything. Like it can cover kind of any polynomial situation you might need, can deal with a lot of these other weird ones. May not always be the best version, but it's usually not lousy. All right. So for the linears, we use the correlation coefficient to decide how good of a fit we had. That was that we used the letter R to abbreviate that, right? That we talked about the R value, the correlation value. For these other ones that are not linear, we use what's called the coefficient of determination. Which is an R squared value. Now remember, if we have something squared, that number can't be negative, right? So basically, as R squared gets closer to 1, the better our fit is. So R squared values close to 0 are bad fits. R squared values close to 1 are good fits. So far, so good. We'll do some examples here in a few minutes, but a little bit more I want to talk about with regard to this power model. So in the power model, we call B we call is the power, and A we call the constant of variation. Or in some texts, they might call that the constant of proportion, depending on where you're reading. I think that we use variation in our text. So let's just do some examples of things that could be considered power functions and talk about their power and constant of variation. Okay? So I'm going to pick on some geometric examples and some real-world examples. So in geometry, we know that the circumference of the circle varies with the radius. So in this case, like my independent variable is R and my dependent variable is C. So what is the power if I think about this as a power function, what is the power for this equation? It's 1. Yeah, it's the exponent on the variable, or the independent variable, which in this case is just 1. What's my constant of variation?
What was the constant variation?
It's 2 pi, yes. So just like the coefficient on the variable. Okay. So we also know that the area of a circle varies with the radius. So again, it's my independent variable and my dependent variable. What's the power for this one? 2. And what's the constant of variation?
1 pi.
Yep. Or we just write pi. It's fine. 1 pi is not wrong. Okay. Chemists, we know that the volume of enclosed gas at a constant temperature varies inversely with the pressure. So again, the pressure causes the volume to change on the gas, right? If you increase the pressure, the volume's going to shrink. You compress that gas down. If you decrease the pressure, the volume of the gas is going to expand and fill the container. Everybody agree with that? Okay. So what's the power in this situation? This one's a little bit trickier.
Would it be 1 or negative?
That's the question, right? What do you guys think? 1 or negative 1? It is negative 1. Why is it negative 1? Because the variable's in the denominator. Very good. Remember that this. You could think about this as k times p to the negative 1. Also means the same thing. And there it's really obvious that the power should be negative 1. And what's our constant of variation then? Okay. So I can color code the rest of this. Okay, we'll do one more example, and I feel like you guys have probably got this. So the volume of a sphere varies with the radius. What's the power going to be here? 3. And what's my constant of variation?
4/3 pi.
4/3 pi. Everybody feeling reasonably okay with this stuff? Okay, that's good. Again, not super difficult, but maybe a little bit new, and don't want to leave anybody behind. All right, what if we ask you to do the reverse? We give you the description of the power function in words, and then ask you to write the power equation Yeah, that's tiny. So let's say we want to write the power function. An object is dropped off a building. Its distance from the ground varies with the square of the amount of time it's been falling. So let's start with what the independent and dependent variables would be in this situation. So we know this is our power model, right? So in this situation, what's our independent and dependent variables representing? So this is something you'd have to get from the reading. Okay, we have distance is one of them, and the other quantity is time. Okay, which one depends on which? Yeah, I think the distance is going to depend on the time. Like how long the object's going to be falling is going to dictate how far it is from the ground, right? So this guy is going to be like our time, and this guy is going to be like our distance. Everybody's okay with that? And then what else? What other? There's one other piece in here that we've been given. What else can we figure out from the statement that's been given here? Yeah. So that's really giving us the power, right? So that would be what you could write as your answer. Those of you in physics should recognize this. What is the actual value for the A here? Does anybody remember? Negative 9.8 meters per second squared, or negative 16-ish feet per second. Just the constant due to gravity. Those of you in physics right now probably recognize the number now that I say it and are like, oh yeah, we've used that. Certainly you've done 1D motion with gravity at this point in the semester. In fact, probably you haven't done it in a while, which is probably why you forgot. If you are currently in the physics class. All right. Let's do another example. Okay. Consider the given data. Use the data, create a scatter plot, and create a power regression to model the data. Then use the curve to estimate the orbital period of Neptune, which is 4,497 gigameters from the sun. Okay. Is this going to really change the process that I'm using at all from what we did in doing the regressions in section 2? No, I'm going to do the exact same stuff. The only difference is when it gets to the regression model, I'm going to do a power regression as opposed to a linear regression, but like the calculator steps are exactly the same. So we'll start by entering data into my calculator. I press stat From the edit menu, I'll pick the edit command. I'm going to go clear out my lists. By the way, if anybody's accidentally deleted a list and needs some help, this will be the last example after that. If you have need some help recovering a deleted list, I can help you do that. It's not so bad, but it's just a heck of a lot easier to just not press the delete button when you're on the list name. But I get it. We all make mistakes. It's not that big of a deal. Okay. So the orbital period, just FYI, is the length of a year, basically. If you think about what you know about the solar system, we know that the planets travel in elliptical orbits. The further you're getting from the sun, the bigger that orbit's got to be, so the longer its year is going to take to do one revolution, right? Not surprisingly, the Earth is 365.2. What's the 0.2 really? That's the leap year. Like every 5 years you get a leap year to make up for that like extra little bit. Okay.
Is this year a leap year?
I don't think so. I think last year was the leap year, wasn't it? 2020? Okay. All right, so we got that entered in, exit out of there. I'm not even going to bother looking at the scatter plot because it told me the kind of regression curve to use. If it didn't tell me, then looking at the scatter plot would be really necessary step. But it told me to use a power, so I'm not going to even bother with looking at the scatter plot. Really, the only point of looking at the scatter plot is to be able to choose the model. So I hit Stat, go over to Calc, and I'm going to scroll down to find the power reg. There it is. PWR is short for power. My x's weren't, well, I guess it should go without saying, but let's take a moment and think about it anyways. The distance from the sun is definitely going to increase the amount of time it takes to run that orbit, right? Everybody agrees that the closer you in, the smaller the circle you have to travel, so it should be shorter. That should be pretty obvious if you think about it, but, you know. Since they are asking me to do a prediction here, right? That's what the estimate is saying. I am going to store this. So to store this into the Y1, I'm going to press vars, move over to the Y vars, pick the function option, and then I'm just going to put it in Y1. Hit calculate. So here is my information. So my power function would be Y equals 0.2x to the 1.5-ish power. Everybody's okay with that idea? And then the R squared tells me that is quite good. Look at that R squared value. Can't get much closer to 1 than that, right? That's pretty doggone good. Okay, so what I want to do is predict the orbital period for Neptune. So I want to do basically Y1 of 4497. I'm going to do this using that function notation method that I showed you earlier, just as a change of pace. And because I didn't bother to create the scatter plot, it'll be quicker to just do it that way. So I'm going to press vars, go over to Y vars, pick the function option, pick Y1, and then do 4497. Holy simoleons! That's a long year. Thank goodness we don't live on Neptune, right? 60,150 days. Ay caramba.
Oh, no. That's a long time.
Just as an FYI, that is 164 years on Earth. Yikes! 1-year-old Neptunian would be super old. But that's the gist of it, right? Now, is this really any different than what we had done in the previous sections. When it comes to the calculator standpoint, not a thing is really different. We got some new names, we got some new regressions. I think for the most part in the homework, it will tell you the regression to use. If you are forced to make a choice, like, hey, which regression would probably be best, what should you look at? You want to look at the scatter plot, right? Look at the shape of the scatter plot. If it looks like a line, linear. If it looks like a U, quadratic. If it looks like a cubic. If it looks like a whoop, exponential. Or if it looks like a whoop, logarithmic. The shape of the scatter plot would be what you'd use to make a choice if you weren't told what to do. And if you were really like, oh boy, is that quadratic or maybe that's exponential because you just have like a little piece of it, maybe both of them would be reasonable. What would you do to tell the difference between which one would be best? You actually would do the regression, look at the R-squared values, right? That would tell you which one would be best.
The one that's best is the one closest to 1.
Correct. Yeah. Yep. So it's, like if you're forced to choose, you look at the scatter plot based on the shape. If 2 of them or 3 of them are like, maybe both of these would be good, I don't know. You can always run the regressions and compare the R-squared values. And then you can make an argument that, hey, look at the R-squared values for this model and this model and this model. This one had the best R-squared value. That's the one I would use. That's a pretty reasonable argument to make. You know what I mean? We'll stop here. You guys can take the rest of your time on class to kind of work on the problem